Have you ever just stopped and stared at a massive, sweeping flyover, or maybe one of those towering high-speed rail viaducts, and you just have to wonder, how on earth do those incredibly long spans of concrete not just snap right in half under all that immense weight? I mean, it honestly seems like magic, but it's not. It is actually one of the absolute most revolutionary engineering concepts of the modern era. So today, in this explainer, we're demystifying prestressed concrete. It is the hidden secret behind literally the sleekest and strongest megastructures in our cities today.
Okay, let's dive right into our roadmap. We are going to cover Section 1, the concrete cracking problem, move to 2, the pre-stressing solution, then check out 3, the super materials needed, compare 4, factory versus on-site systems, and finally hit 5, building modern infrastructure.
All right, first up, Section 1, the concrete cracking problem. So, to really appreciate the absolute genius of pre-stressed concrete, we first have to understand the historical limitation of ordinary concrete, a problem that engineers battled for well over a century. Let's start with a really simple thought experiment. Picture a standard ruler, just a normal plastic or wooden one. If you hold it horizontally at both ends and press down right in the middle, what happens? Well, obviously it bends downward, it deflects. But physically, two totally different things are happening at once. The top fibers of that ruler are squeezing together. That's what we call compression. Meanwhile, the bottom fibers are actually stretching out, going into tension. And if you press hard enough, that bottom part will crack, and the whole ruler just snaps.
Now imagine replacing that ruler with a plain, unreinforced concrete beam. Concrete is an incredible material when it comes to compressive force. I mean, it literally loves to be squeezed. But it has a fatal flaw. It is extremely weak under tensile force. In fact, concrete's tensile strength, its ability to withstand stretching, is only about 10% of its compressive strength. So about 150 years ago, engineers came up with a pretty clever workaround. They invented reinforced cement concrete, or RCC, simply by placing steel rods down in that tension zone at the bottom of the beam. The steel stretches, it takes the tension, and it keeps the beam from collapsing. Problem solved, right?
Well, actually no, because here is the massive catch with ordinary RCC. Cracking is actually permitted and expected. When a bridge beam cracks a little bit every single time a heavy truck drives over it, water inevitably seeps into those cracks. Then the internal steel begins to rust, the beam starts to deflect more, and the entire structure ages way faster than it should. We are essentially building structures that are pre-damaged before they even see their full everyday load. And for the sleek, modern megastructures we want to build today, relying on heavy, cracked, and bulky beams is just completely unacceptable.
Which brings us to Section 2, the pre-stressing solution.
That exact limitation, the cracking, is what drove engineers to completely rethink how we build, and it led to the revolutionary idea of pre-stressed concrete. The fundamental principle here is incredibly simple, yet it's deeply profound. It really all comes down to this core idea from our source material. We deliberately induce internal stresses in the concrete before the external load is applied, so that when the load comes, the internal stress counteracts the external load.
Okay, that sounds a bit academic, so let's break it down using something you might literally have sitting in your kitchen right now. A tiffin carrier, or one of those stacked metal lunchboxes held together by a long central rod. When you tighten the nut at the very top of that rod, the rod stretches into tension, and at the exact same time, it squeezes that whole stack of metal boxes together, forcing them into compression. Now, imagine those metal boxes are individual concrete blocks. Because you've tightened that rod so much, those blocks are in a permanent state of intense compression. If you grab the blocks and try to pull them apart, applying a tensile force, they absolutely will not separate until you pull harder than your initial squeeze. That is pre-stressing. Engineers stretch high-strength steel wires with massive hydraulic jacks, anchor them, and then let the steel try to shrink back. The concrete stops the steel from shrinking, meaning the steel stays in tension, and the concrete is permanently locked into a powerful, unbreakable compression. Let's move on to Section 3, the super materials needed.
Of course, if you are going to put concrete under that much immense squeezing force right from day one, you absolutely cannot use ordinary everyday materials. You need super materials. In normal RCC, engineers use M20 or M25 grade concrete, which handles about 20 to 25 newtons per square millimeter. But in pre-stressed concrete, because we are squeezing it with such insane forces, we have to use M40 to M60, sometimes even way up to M100 grade concrete. If we used ordinary concrete, it would literally just crush under the pressure. And the same goes for the steel. Standard RCC uses mild steel. If you stretch mild steel, it behaves kind of like a cheap rubber band. It stretches out, but it doesn't completely return to its original shape. For pre-stressing, we need steel that can be stretched a massive amount and still spring back with intense, violent force. So we use high-tensile steel, which boasts an ultimate strength of 1,600 to 2,000 newtons per square millimeter. That is a massive upgrade.
And this high-tensile steel comes in a few specific forms, depending on the actual job. You have your individual wires, which range from 3 to 8 millimeters thick, but much more commonly, especially if you look at major bridges, you'll see strands. These are multiple wires twisted tightly together to give even greater strength. And for the absolute heaviest jobs out there, we're talking nuclear power plants or incredibly massive heavy girders, engineers bring in the big guns, thick 32-millimeter high-strength bars.
Now for Section 4, Factory versus On-Site Systems.
So, we have the theory, and we have our super materials. But how do engineers actually pull this off out in the real world? Well, there are two fascinating ways they achieve this. System 1 is called pre-tensioning. Picture a super long casting bed in a factory. They stretch out the steel wires tight between fixed points, pour the fresh concrete right around those tight wires, and just let it harden. Once the concrete is fully hard, they literally take cutters and snip the wires at the ends. The steel tries to snap back, but since it's bonded to the concrete, it instantly puts the whole block into compression. This is absolutely perfect for things like railway sleepers and precast girders. Then you have System 2, which is post-tensioning. This happens right on the construction site. You cast the concrete first, but you deliberately leave hollow tubes or ducts running inside it. Once that concrete is hardened, you thread your steel through those ducts, hook up hydraulic jacks, and stretch the steel against the hard concrete itself. You anchor it tight, pump in some cement grout to fill the space, and boom, you're done. This is the go-to method for major bridges and massive flyovers.
Finally, Section 5, Building Modern Infrastructure.
Understanding these two systems lets us step back and really appreciate the breathtaking scale of what they make possible today. Take the Mumbai-Ahmedabad bullet train project, for example. The viaducts for that train require concrete girders that can span 30 to 40 meters without any intermediate supports at all. Ordinary RCCs simply cannot do that. It would have to be ridiculously thick and impossibly heavy. Or look at the massive river bridges stretching over the floodplains in Bihar and Assam. Pre-stressing allows engineers to factory cast individual segments and literally launch them out over the water, which drastically speeds up construction time. And all of this relies on really rigorous engineering standards codified in India's IS 1343 code. First introduced back in 1980 and revised for the modern era, it acts as the definitive rulebook for this engineering marvel.
Okay, time for a quick math challenge. Don't worry, it's easy, but it perfectly proves the concept. Imagine you apply a compressive, squeezing force of 10 newtons per square millimeter right at the bottom of a beam. Then a huge external load, let's say a bullet train, rolls over it, and that tries to create a pulling, tensile stress of 8 newtons per square millimeter at that exact same bottom fiber. The million-dollar question, will the concrete crack?
The answer is 0. Absolutely no cracks at all. Because 10 units of initial compression minus the 8 units of tension from the train still leaves you with a positive 2 units of compression. The concrete literally never even experiences tension. It doesn't even have a chance to crack. That is the sheer magic of pre-stressing. The entire section acts like one rigid, solid block of steel-like strength.
It really all boils down to this incredible quote from our source material. In RCC, we let the steel work hard. In pre-stressed concrete, we make the concrete work hard before the load even arrives. Instead of building structures that basically sit there waiting to be damaged by the forces placed upon them, we proactively arm the concrete to fight back. It's a total paradigm shift. So here is my final thought for you. Next time you're stuck in traffic or just commuting through your city, I want you to look around. Look closely at a railway overbridge or a brand new flyover. Ask yourself, is that beam deep and incredibly bulky? Or is it shallow, spanning a massive distance and remarkably sleek? Because if it is shallow and elegant, you are looking directly at the invisible magic of pre-stressed concrete holding up your city. Keep questioning the world around you, and thank you so much for joining me on this explainer.